Today we're going to start talking about balancing chemical equations. We're going to get lots of practice with this, but I want to start by talking a little bit about what the idea is for balancing equations. And when we're talking about balancing equations, it might be helpful to you to think about an old pan balance. I don't know if you've ever used one of these, but they have two pans, and they have this little arm connection in between them. Pardon the crudeness of my drawing here. And these arms, they can move up and down based on what you put on them. So the idea for our balancing is that when we have a chemical reaction, which we're going to represent using some symbols by putting over on the left-hand side the reactants, the things that we're starting with, and then we'll put an arrow, and then we'll put a detail of all the things that are made, which we're going to call products. So our standard chemical reaction is going to be laid out like this: reactants on the left-hand side, products on the right-hand side, and an arrow indicating the direction that this reaction is going to go. So the key here is that matter can't be created or destroyed. This is the law of conservation of matter, or conservation of mass. And this is fundamental to what we're doing when we're balancing these equations. Because the idea is that whatever matter, whatever elements we have on the left-hand side, on the reactant side, have to turn into products on the right-hand side. And that, remember those early principles, John Dalton pointed out that all of the atoms that are starting in a chemical reaction, none of them get destroyed. They just get reorganized when we put them into products. So let's take a look at an example reaction here. A reaction of carbon and oxygen gas. So carbon is the simplest way of talking about, for example, coal. Coal is usually a mixture of things, but it's mostly carbon. Oxygen gas is available in the atmosphere, and so when we burn carbon, ideally we're turning it into carbon dioxide gas. And I say ideally not because carbon dioxide is a great gas right now, but just because if we burn it and make carbon monoxide is a toxic gas, and so that's probably a little bit worse. Anyhow, so if we have this simple reaction where we have carbon reacting with oxygen to make carbon dioxide, let's do a count. We have one carbon atom on the left-hand side right here. We have one carbon atom on the right-hand side right here. We have this 2, which indicates that we have 2 oxygen atoms here on the reactant side. And we have 2 oxygen atoms here on the right-hand side. So the same number of atoms appear on the reactant side and on the product side. The other thing we can't do, we can't just have 3 of any particular kind of atom. We have to have 1 carbon and 2 oxygens. We can't convert a carbon into something else. So I couldn't go carbon dioxide turns into nitrogen dioxide. That wouldn't work because I'm not converting a carbon into a nitrogen. If I have a carbon on one side, I need to have a carbon on the other side. And so this one carbon balances out with another carbon because we know that carbon has a specific mass, right? The average atomic mass for carbon is 12.01 grams, or excuse me, atomic mass units, since we're still just talking about atoms. And then we have 2 oxygen atoms. Each one of these has an atomic mass of about 16 atomic mass units. And so the mass of an oxygen has to balance with the mass of another oxygen. And so these 2 sides would be balanced when we think about those masses and when we think about the atoms not being created or destroyed. So when I talk about balancing chemical equations, what I'm talking about is when people talk about a reaction and they say, we're reacting, let's say that we are reacting some, we'll go with yet another carbon-hydrogen compound like methane, another fuel. We're reacting methane with oxygen. And I'm putting in phases of matter, but right now it's not super important that you do that. And let's say that our reaction with methane and oxygen is going to make carbon dioxide gas and also water vapor. Because this is a burning reaction, it's going to be hot. So I use an inventory method to balance equations. This is not the only method that's around. It's a nice systematic one, and it will prevent you from making mistakes. So I recommend you to try it, but I'm actually also going to link an algebraic method. If you really love algebra, you might really enjoy the algebraic method. Either of these methods will work, and there's probably more that will work as well. So if you have a method that will always work for you, doesn't involve any shortcuts, you're welcome to keep doing it. But I will recommend that you give a serious look at this inventory method or at the algebraic method and try them out, because both of these methods will work every single time. If you're using a shortcut method, they may not work every time. All right, so what I'm talking about when I mean an inventory is that I'm going to pay attention to both the reactant side and the product side. And I'm going to take a little inventory of what I already have. So I'm going to count these up. And I like to put my elements in the same order so it's easy for me visually to say, oh, here's how many carbons I have and here's how many carbons I have, for example. So I can see I have carbon, hydrogen, and oxygen. So I'm going to put them over here on the reactant side. And I have carbon, hydrogen, and oxygen. So I'm going to put them in the same order. And then I usually will put some little colons here, but it doesn't really matter. So for each of these, I'm going to take an inventory of how many I have. I have 1 carbon. I have 4 hydrogens, which I'm looking at the formula unit or the molecular formula to tell me how many of each element I have. If you're still working on that, please let me know, and I'd be happy to work with you on it. So I have 2 oxygens. And then over on the right-hand side, I have 1 carbon. I have 2 oxygens here and 1 oxygen here, so that makes a total of 3. And then I have 2 hydrogens right here. Now, when I take some strategy, I'm going to put some tips right here. For strategy for balancing equations, it's usually better to start with either not hydrogen or oxygen. We don't have too many choices here. Or an element that only appears once on each side. And when I say on each side, I mean on each side of the arrow. Okay, so let's take a look at our equation again. Carbon appears in only one place, so let's check. I said it's better not to start with hydrogen or oxygen, but carbon is already balanced, so we don't actually have to do anything with carbon. So let's go on to our next elements. When we look at hydrogen, hydrogen is in 1 compound on the left-hand side, and it's in 1 compound on the right-hand side. Compare that to oxygen, which is in 1 compound over here on the left, but it's actually in 2 places here on the right. So I'm going to take my tip 1A here, and I'm going to say, all right, since, 1B, since my oxygen appears in 2 places over here, I'm going to keep things simpler, and I'm going to start by looking at hydrogen. So when I look at hydrogen here, I can see that there are 4 hydrogens on one side, and there are 2 hydrogens on the other. And so here's another note, is that we can only increase numbers, not decrease numbers. And I'm talking about numbers of atoms. So if I'm looking at 4 and 2, I want to make sure that I get the same number of hydrogens on both sides. But I can't go down, so I can't make this 4 into 2. I have to make this 2 into 4 instead. So if I'm going to make this 2 into 4, I can multiply it by 2. But if I'm multiplying it by 2, I'm actually not just multiplying the hydrogen by 2. I'm multiplying the whole thing of the compound that involves hydrogen, which is the water. And that means that I'm going to be putting a 2 in front of that molecular compound. Okay? So when I put a 2 in front of this, that means I really have 2 water molecules. So I went from 1 to now having 2 water molecules like this. So now when I count up all of my atoms, I can see I have 1, 2, 3, 4 hydrogens, and I have 1, 2 oxygens right here. But don't forget, oxygen was in 2 places. I have 2 oxygens right here as well. So I need to add these 2 oxygens and these 2 oxygens to make 4 oxygens. So after I have double checked on my right hand side and I've made sure that all of my counting is good, so I just double checked here. Here I have 1 carbon, 2 oxygens, and now 2 more oxygens is 4. And then I have 2 times 2 is 4 hydrogens. Okay, so my right hand side is correct. Now I have the same number of carbons. I have the same number of hydrogens, but I need to look at my oxygens. So my oxygens, I now have 4 on the right-hand side and 2 on the left-hand side. I know what to do. I can take the smaller number and I can get to this multiple. 2 times 2 is 4. And when I take this 2, it means that I'm putting a 2 in front of this oxygen molecule so that the whole oxygen molecule is multiplied by 2. I really have 2 O2s now. So I have a total of 4 oxygens. Now my carbons balance, my hydrogens balance, and my oxygens balance. And I'm all set with having balanced this equation. So the goal of balancing an equation is to get the same number of each atom on both sides. Let's go ahead and look at another example. This is H2S reacting with oxygen to make S8 and water again. Okay, so here's what I want you to do. I want you to make an inventory. And then I want you to start with sulfur. And I want you to try balancing. So pause the video, make your inventory, start with sulfur, and try balancing this equation to see if you can come up with the right answer. All right, hopefully you took time to do this yourself. I'm going to go ahead and work it through and explain my steps, and you can check your work. So on my reactant side, I'm making my inventory. I have hydrogen, sulfur, and oxygen. I have 2 hydrogens, 1 sulfur, and 2 oxygens. On the product side, I have 2 hydrogens, 8 sulfur, and 1 oxygen. I suggested that you start with sulfur, so that's what I'm going to do. So I have S8 over here and I have 1 S over here. So I want to get to 8. So I need to multiply this by 8. I'm going to do that by putting an 8 in front of the compound that has sulfur in it. But I noticed that this also has hydrogen in it, so I need to update that hydrogen to 2 times 8, which is 16. Okay, so I've updated this. I now have my sulfurs balanced, but I need to check on my hydrogens and I need to check on my oxygens. Okay, so we've got 16 hydrogens here and 2 hydrogens over here. So let's go ahead over on this right-hand side and multiply that by 8 to get 16. So that means I'm going to put an 8 in front of the water molecule. This will give me 16 hydrogens, and 8 times 1 is 8 oxygens. So I have balanced the hydrogens, and now I need to look at the oxygens. This has 8 This has 2. I know that I can multiply 4 by 4 to get to 8. So my multiplying by 4 means I'm going to put a 4 in front of the O2 here. And that's going to get me to 8. Now, once you have done this, you can always go back and recount everything. And it's always a good idea just to make sure you haven't missed something. So when I go back through, I'm going to say, all right, 8 times 2 hydrogens. I have 16 hydrogens here. Now over here, 8 times 2, I have 16 hydrogens over here. 8 times sulfur, which is 1, that's 8 sulfurs over here. S8, I already have 8 sulfurs over there. And then oxygens, I have 4 times 2 is 8 oxygens. And 8 times 1 is 8 oxygens. So I have double checked my work, and I have confirmed that this is a balanced equation. So some balanced equations, or some equations, are going to be a lot easier to balance, and some are going to be a little harder to balance. And this inventory method, occasionally, it's hard to see what direction you're going to go. So these ones that I've been using, I've been trying to make them be reasonably simple or straightforward so that I just can kind of go back and forth, increasing one and not the other. But occasionally you will get to a situation where you have a pretty complicated scenario where you have elements showing up in multiple places. And in that case, it actually would probably be a really good idea to use the algebraic method instead. Now, I only just learned about the algebraic method today. I was looking at another professor's resources, and I thought, I wonder if he has balancing equations on it. And sure enough, he did, but he's using a totally different method that I've never seen anybody use before. So I was really excited about it, and I'm going to share it with you. But I also want to encourage you to just stick with a method that works. So if you really like the inventory method that I've shown you, it will work. And so go ahead and stick with it. If you really like a different method that you've learned in the past, I encourage you to have a conversation with me about it and just make sure that there aren't any shortcuts that are going to occasionally cause you troubles in the future. I'm going to go ahead and post a couple more example problems for you if you want to give them a try before going off and working on the worksheet. So here's 2 example problems. The first one is CH3SH plus CO goes to CH3COS CH3 plus H2S. The second example is P4 plus O2 going to P2O5. Now, I encourage you to stop right here with the video and go ahead and try these out yourself. I'm going to put the answers up here in just a moment here, but pause it so you don't get a spoiler, and then come back and finish the video the last couple seconds. All right, I hope you paused it and you took care of these. It turns out with this first reaction, all you have to do is put a 2 in front of the first chemical. With the second, you need to multiply oxygen by 5 and P2O5 by 2. If you have any questions about the answers here or any of the other balancing equations, please let me know.